special pleasure to be able to welcome Keith Devlin back to the University of Huddersfield. His engagement with the University of Huddersfield has been an important element in our determination to emphasise the importance and fascination of mathematics, as he provides an answer to that tantalising question, what do mathematicians do now that machines can do all the maths? Will you please join me in welcoming Keith to the podium?
The first thing about being here is everybody around me sounds like me. The reason I have a personality in the United States is I sound different from most of the people on National Public Radio. I'm pretty sure the reason I became a math guy way back in '94, when I was just a talking head on a Saturday morning magazine show, was it turned out that putting me on for a quarter of an hour on a Saturday morning with a Yorkshire accent, they just thought it was wild. You know, the most common thing was I didn't understand anything you said, but I really liked the accent. And I've been milking that ever since, and hopefully I've figured out how to get the message through despite the accent. And actually this is a talk that I finalised. I retired officially a year ago, Christmas last year, and I founded this Stanford Mathematics Outreach project at that time. It's the thing that keeps me connected with Stanford. It's what I'm doing. I direct this as a volunteer largely for Stanford. Okay, this is where I'm beginning. There was a mathematics, our impression of mathematics built up over the 3,000 or 4,000 years that it was being developed. And the only way to do it was to learn how to do calculations. It was the price we had to pay to get into mathematics. Mathematics never was calculations. Calculations were the bricks. Mathematics was the building you built with those bricks. But you couldn't build a building until you knew how to put bricks together and put cement between them. So you had to learn all of the mechanics to get into that, to create the buildings. But the mathematics was really the architecture. Building buildings, building spaces out of the bricks of calculation. But you had to do the calculations. And that was the same for thousands of years. But that is deliberate. The tense in that is correct. That's the price we had to pay. You know, it's hard to realise it if you're not in the business. But mathematics in 1990, actually in 1989, actually, strictly speaking, 1987 was the revolution. A revolution was started in 1987, October 87, that by 1990 had completely changed the landscape of mathematics because we no longer had to do any kind of calculation. That's now history. And by calculation, I don't just mean numerical, I mean any formal procedure. Solving equations, inverting matrices, differentiating, integrating. If there's a procedure, it got outsourced to technology. And we outsourced, by 1987, we had tools available where we could outsource anything that was procedural. Well, that was more or less all the stuff that we learned right through your undergraduate degree and beyond. All that became automated. Here are some of the tools that came out. I said October 1987, which was actually the year I went over to Stanford. Within 2 months of arriving there, Steve Wolfram, a physicist from, I think it was Caltech he was at the time, launched the first version of Mathematica, which was the first system that did it all. It did all of the mathematics that was procedural. He implemented all of those procedures as efficient algorithms. Maple came out in Canada around the same time, a little bit later. Wolfram Alpha is a very friendly version of Mathematica, which makes it very quick and easy to use these tools. MathWorks is another one. There are a few more, but I mentioned those. Now, I've included this because that's still a powerful device, and in many parts of the world, that is the most powerful device. So we have to include that. It's not as versatile as these, but that thing packs a lot of punch these days. So these are the tools that we outsourced calculations of all kinds. Okay, with that background, that's where I'm going to be going. I'm going to be talking about what that revolution, 1987, it started. By 1990, in the business, it was over. Everybody had changed the way they did mathematics. But by way of sort of motivating where I want to go with it, I want to start with this building, which I hope you have seen in for real. It's the cathedral in Florence. You absolutely should see it as soon as you can. It's a wonderful building. It took 140 years to build. Beginning in 12th, 13th, 14th century was that period. That was 140 years to build this wonderful cathedral in Florence, in Tuscany, one of my most famous places. both as a mathematician and as a road cyclist. Italy is great for both. Here's another building that is regarded as one of the world's most beautiful buildings, the Opera House in Sydney. That was built in 14 years. 10 times faster to build that one than that one. So the question is, how were they able to build it 10 times faster in more recent times than back in the 13th century, around that time? Well, it's the same problem. It's building a big building that's attractive to look at, that serves the functional requirements, requires sound construction. So in a sense, nothing has changed. It's big buildings. It's creating a big building that meets human needs and that people find attractive and enjoy being in. All the principles are the same. The laws of physics are the same. I mean, we know more of those laws now, but they are the same laws. The laws of materials are the same. I mean, concrete, cement, I mean, all of the stuff that you build with and the basic principles are the same. So it wasn't because, I mean, there are now new materials, but that wasn't the essence of what changed. This is what changed. A completely different collection of tools for building. Lots of stuff that had to be done by hand became automated. And when you have a lot of different tools, you can do things much faster. The basic principles are still the same. Those tools have to follow the same basic principles of design and aesthetics, but they allow you to do it faster. Not so much different, as faster. And as a result of new tools, it means the architects and the builders today have to have a completely different skill set. They don't have to have all the skill sets of stone masonry and chipping away blocks and things. That's all gone, it's all automated, you have big machines that do things. So it's a very different skill set. In some sense, it's the same skill set. At the higher level, it's the same. But down at the coal face, or the concrete face, of actually constructing these things and designing them, it's a very different skill set. So it's the same, and yet it's very different, and that allows us to speed it up. Well, that's architecture, but I've already connected architecture and buildings and things with mathematics, and the mathematics is in the same situation. It was the tools that changed it, that led to the change. And here are some of the tools that are now at our fingertips for mathematics. This is actually my toolkit with a couple of amendments. When I work on a problem, and since I went to the States in 1987, I went to the States, 2001, after the September 11th attacks, I started working for the Defense Department, first in the NSA, then the US Navy and the US Army, on very applied projects using my experience in mathematics to try and improve intelligence analysis for different branches of the Department of Defense. And this is the toolkit that I found myself using more or less in the order of importance. The number one tool for a mathematician, almost anyone today, is Google. It stops you reinventing the wheel. It quickly allows you to find everything that's been done, or lots of things that have been done. It allows you to find the names of people you want to contact. Within a half an hour or an hour, you can get a good overview, providing you know what words to put into Google. There is skill involved in using these tools. These are not skillless tools. Unless you can put the right search terms into Google, you're going to be wasting a lot of time. But if you know what words to put in, you can quickly find a lot. So I use Google. Google usually returns some things that I've learned as an undergraduate and forgot. All sorts of things come up. So with Google, I find that I have to go to Wikipedia and look up explanations of some of these things. I've found that Wikipedia is actually the best resource, because in higher mathematics, only an expert can contribute. So there's no question about, can I trust it with Wikipedia? It's almost always right, because only experts contribute to those things, except for school mathematics. There's all sorts of weird stuff there. But for higher mathematics, you can get good descriptions on there. But even if that didn't give it, there are other tools. Because I've been in the business for a long time, I use email, and I email people, and because I've got a Stanford address, people read my email and very often reply. YouTube is a very good way to get mini lectures. You know, you can find out in a 20-minute lecture for almost anything under the sun, even extremely obscure and advanced. Wolfram Alpha, I'll mention that a little bit later. That's my tool of choice for doing the procedures. If I've got a procedure that I need to start to use, Wolfram Alpha is where I go, because the interface makes it as easy to use as Google. It's a similar sort of interface. You just type something in. It has very sophisticated parsing algorithms to make sense of it. Spreadsheets are useful for getting a sense of sizes of problems. I actually don't use MATLAB, but I wanted to just show that there are other tools available that can be used. I don't use MATLAB because I was around when Mathematica came out. I was one of the advisors when it came out, and for a long time they provided me free copies, so they bought my allegiance for life. I have to buy them now, but they've still got my allegiance. Math Overflow is good for getting nerdy answers to nerdy questions from anywhere in the world. I don't use the calculator anymore because Wolfram Alpha does that and more, but it's still a valuable tool. And there's one tool that I use that's extremely important when the going gets tough. 90% of the time, I think, using these tools, using the first 2 or 3 of them, I've sort of solved the problem because some smart person in the world has done it. And I've found out, and I send an email and I get a PDF of a paper. But sometimes it doesn't work. And that's when this tool is used. That hasn't gone away. In fact, that's when it gets really interesting, because that's when I can feel justified sending the invoice for my consulting time. Because if I don't get to that, I've brought value, but I've only brought value as a node in a network. But if I need to use that, I'm bringing value as a contributing person in the research. So that's when I get excited. But most of the time, it's just a matter of finding out that somebody else has done it. And if they've done it, waste of human resources to redo it, except insofar as that gets you into the problem. Okay, so those are some of the tools, and as I say, that's my list, and I've given this kind of talk to many audiences, and most of the practicing mathematicians or engineers in the audience will say, yeah, my tool set's sort of the same, but with different emphases. Okay, so the question then is, if we have tools available, and almost all of those are free. I mean, Mathematica is kind of expensive, but the others, Wolfram Alpha, there's a paid version, but the version that's free in the cloud, you can use it your smartphone to get into it. It does almost anything you need to do. Okay, so does that mean we no longer need to teach calculation? No, not even close. What's changed is that we're no longer to teach it in order for people to be able to do it fast and accurately. You know, the way we think of mathematics was heavily influenced by the Industrial Revolution around this part of the world. You know, when you had large factories with lots of people doing things that involved some planning, some number work, you needed lots of people to do the computation. You know, there was an internet for many decades. It was people who communicated and did calculations. So the nodes of the computation were people. And our education system was shaped by the needs for having lots of people who could follow instructions and follow rules and execute procedures, because that was how it was done. And the education system was developed very largely to meet that need. But that's gone now, because all of that stuff is done by machines. And it's not just that machines are faster than people. They almost never make mistakes. People make mistakes all the time. The machine can handle 1 million variables. Humans have trouble with more than 3 variables. You start to make mistakes. You can no longer visualize it if you've got 4 variables, because you're beyond geometric intuition. People are very limited. They're slow, they make mistakes, limited to a small number of variables in the equations, and can only deal with small data sets. Computer will handle any size data sets, and today's problems usually involve lots of big data sets. So it's not just that we can outsource them as a principle. There are practical reasons why it makes sense. They're just better at it than we are. The only reason we didn't use them earlier was they weren't available. So we no longer need to teach people to be accurate or fast. That's gone. But they do have to use a machine. You can't use a machine or a tool unless you know something about what it wants to do and putting all of the pieces together. So that means we have to teach actually more or less the same old stuff. The arithmetic, some geometry, some trigonometry, some calculus, all of that's still there. But it's got to be taught for understanding. You know, I mean, I got through most of my undergraduate degree by being able to answer exam questions very fast. I realized quite early on as an undergraduate, I didn't need to understand almost anything so long as I could answer the questions. Then I became a graduate student. I was TAing, I was teaching at Bristol, and I was assisting with undergraduate students. And my job then was to explain the mathematics to the students. And that's when I realized I didn't fully understand things as much as I should have done. And I actually learned a lot of the understanding in mathematics as a graduate student teaching it, because the best way to understand anything is to try to teach it. Well, now things have changed. You shouldn't be able to pass an exam unless you really understand it, because if you can pass an exam without understanding, you're just doing what a computer can do, only you're doing it more inefficiently. So we have to get the understanding, but you still have to have that understanding. It does mean going through the same material, but in a very different way, with a very different goal. And this is the different skill set. This is the skill set. The builders of Sydney Opera House, they needed to know how to use big machinery, big stuff, systems thinking, lots of people coming together, doing complicated things, communicating, communication skills. That's a very different skill set. You know, when I was an undergraduate, the way to do mathematics was ignore everybody else and do it. That doesn't work anymore. It didn't work when I was working for the NSA or for the Navy or the Army. This was a multidisciplinary team. It was all about communication. So it's a very different skill set, and it's a community, team-oriented skill set, but still needs that understanding of the mathematical concepts. A way I often like to sort of describe this, to sort of create a memory, an image, and this is the image I'd like you to take away if there's anything I'm saying that's new to you, is in the days when I learnt mathematics, and people of my generation learnt mathematics, and a couple more generations, learning mathematics was like learning to play instruments. First of all, you learnt the arithmetic instrument. Then you learnt the geometry instruments. And then you learnt the trigonometry instruments. And then the algebra instruments. And the differentiation instrument, the integration instrument, the probability theory. You kept learning more and more instruments. And by learn, I mean you had to practice them. You had to become fluent in them. Hours of repetitive practice, learning how to play each of those instruments so that you could use them successfully in working on problems. That's what it was. You were playing all of the instruments in the orchestra in order to be able to do a mathematician. The more instruments you could play well, the more your career progressed in mathematics. So that was the model for thousands of years of learning mathematics. Instruments in an orchestra. Today, that's the mathematician. You're conducting an orchestra. All those tools are just digital instruments in the orchestra. You don't have to learn any of them. You have to learn how to conduct them. Now, can you conduct an orchestra if you don't understand music deeply? No. Is there a successful conductor who isn't really good on one instrument and okay on a bunch of other instruments? No, they're all good. They're world-class musicians. You've got to become really good at one instrument at least to be able to conduct. And you've got to have a good sense of what every single instrument can do, its limitations, its capabilities, how they combine. That's sophisticated stuff. You actually have to know more because you have to understand all of those instruments instead of just being an expert at the cello or the horn or whatever. You couldn't get by as a conductor only by knowing about one instrument. You have to know about them all. This is the same today. This is sophisticated stuff. Conducting this orchestra is not just pushing buttons. It's which buttons you push, when you push them, and how you push them. And that's a lot of skill required to do that. So there's the orchestra. That's my orchestra. That's the one I conduct. And it really does feel like conducting. You bring them in, you bring them out, you fade them up, you fade them down, you mix them, you do novel things with them, you do the same old things with them. And occasionally I have to get my paper and pencil out and essentially create a new instrument that does something different. Okay. Some of the tools you need have been enumerated. People who've studied this in the last 20 or 30 years have sort of written down some of the things that you actually need to know now that would never used to be emphasized. This one wasn't emphasized before 2001 because nobody had talked about it. It was a notion that was introduced in order to help children with learning disabilities learn mathematics. And the people looking at this said, well, if they've got difficulty learning these algorithms because of problems with the way their brain works, it may be dyslexia, it could be something else. But if they have some problem, some inhibitor towards learning, if you want them to learn mathematics, you have to go down to the level of what they said was Numbersense, which was sort of where numbers meet the human brain's capacities. And it's, as I say, it was introduced at this time as a way of teaching, helping people with learning disabilities. It turns out that this is a key skill for being able to conduct the orchestra. The orchestra conductor has to have music sense. One of the things you need in mathematics is number sense. This is the definition from the original paper. There was somewhere in Texas, some university, I forget which one now. Fluidity, flexibility with numbers, a sense of what numbers mean. So this is the numerical side of mathematics. There's equivalences of this in other parts of mathematics, but this is the numero uno one that was looked at first, and there's been a lot of studies of this from various perspectives. Understanding how it works, how things fit in with the real world. It takes a long time to get there. You can't get there by just reading about it. You can only get there by doing it. You can't become good at tennis without practicing tennis. And you can't become good at this without doing lots of arithmetic. But it doesn't matter if you can't get the right answer, which I wish was the case when I was a kid, because I was never able to be good at getting the answer right. When I was department chair and I had a secretarial help at the university, one of the things that secretary realised early on was she should check my exam grading because my arithmetic was terrible. So I'm living walking proof that you don't have to be good at arithmetic to be thought to be good at mathematics. Okay. You need deductive reasoning skills, creative problem solving, but this could go on. Certainly you need algorithmic reasoning. You need to be able to sequence operations, sequence about things. Part of conducting this orchestra is putting things together in the right order and making them do things together. That's essentially algorithmic reasoning. All sorts of metacognitive skills about problem solving. And the list could go on. But the thing is, these are about human capabilities. These are things that the human brain evolved to do, whereas calculation was not. Symbolic manipulation wasn't. We only invented numbers about 8,000 years ago. That's relatively new stuff, the idea of abstract numbers. Most of mathematics is 200 or 300 years ago. So that was all relatively recent. The brain had to be trained to do that. Learning mathematics is in large part boring and tedious and is challenging anyway, because the brain doesn't do it naturally. But these are things the brain does do naturally. So we're now using capabilities that, in a sense, our brain they've always been in the brain, but we're now able to marshal them. Because the thing that was difficult, the calculations and the procedures, we've outsourced to things that do it much better, that will do exactly what you want them to do. So the focus has to be thinking. It's got to be about people thinking. That's what we want to create in education in mathematics. People who can think about the world, and the world could be mathematics itself. Everything I say can be turned in on mathematics. This is not just applied mathematics. Pure mathematics is just mathematics applied to the domain of mathematics itself. So everything I say holds for pure mathematics with a few modifications. But in any case, the focus should be on the thinking, not the procedures. Okay, so how do today's mathematics professionals work? What do they do? I mean, I've said that this is what we need to do, and these are some of the tools. But what thought processes do we do? I mean, we don't just search for stuff on Google, but something else is going on. But the way to answer that is to say, well, what is the role of mathematics in the grand scheme of things? Why did we invent mathematics? How does it fit in with the rest of the world? So why did we invent mathematics? It wasn't to do that kind of ridiculous sum. What is the use of it? How does it fit in with the world? Well, it fits in this way. Okay. And this goes back to the very beginning. If you know about the history of mathematics, you'll be thinking about Aristotle when you see what's coming up next. But going back to the beginnings of mathematics, this is how mathematics has always arisen, how it's always been used. This is the essence of mathematics as it fits into society. Okay. We begin with some real-world situation. Could be anything. I'll give an example in a minute. Maybe it's building Sydney Opera House. Or let's bring Sydney Opera House down to a more familiar scale. The example I want to use is remodeling a bathroom, because most people who own a home have to remodel a bathroom very, very quickly. But the method works this way. You have some real-world situation. You can then express it in a technical language. If it's a medical situation, it's the language of medicine. If it's a law enforcement situation, it's the language of law enforcement. If it's a legal situation, it's the language that lawyers use. There are all these specialized languages that allow us to give us technical descriptions in chemistry, physics, biology, music, law, geography, all sorts of things. We tend to call them disciplines. So there are ways of technical languages that can be used. And then in many cases, you can take it a step further and abstract it into a mathematical description in terms of numbers or particular shapes or whatever. And then once you've got a mathematical description of that real-world situation, you can do the mathematics and you'll get some results, precise results about this domain that you've started looking at. And then when you've got those results, you can feed them back into the world and do something in the world, and around the cycle you can go. Okay, so the example I said I'd use is remodeling your bathroom. So there's your bathroom, it looks like a disaster. There's your real world situation. So what do? You call a local contractor. The contractor comes in and talks to you and sort of, and you just describe, this is a mess, you want this, but that contractor then figures out what you want in the sense of whether you want this kind of bathroom, whether you want those kind of cabinets. So your general ideas, and maybe some photos you've picked up off the web, get turned into the contractor's language about building things, how you build them, the various, whether beams need to go here, whether you're taking walls down. And then there's a technical description. In the case of a big building, this will be a very formalized thing. In the case of the contractor in your bathroom, it'll just be a few notes that he scribbles down about what exactly is needed. And then either that person or that person's employee or that person's spouse will come along and turn that into some mathematics, some spreadsheets, and then you'll hand up with some diagrams. The diagrams will look like trigonometry. There'll be trigonometry, trigonometric diagrams, some spreadsheets, some figures, costing the whole thing. You've got a mathematical description. Your general idea has become a building idea, has become a mathematical idea in terms of spreadsheets and diagrams and so forth. And then the mathematics gets done in order to cost it, to find out how much materials you'll need, come up with a time estimate, etc. So now there's some hard numbers coming out. Those are presented to you. At that point you panic and say, I can't afford that. So you've got some feedback, which is going to have to go around the cycle again. And most bathroom remodels go through the cycle at least 3 times before you agree on exactly what you want to do. But you're playing through this cycle. And then eventually the feedback comes and there's your new bathroom. That's a very homey sort of example, but that's the same for Sydney Opera House, for the cathedral in Florence, for NASA putting up space rockets. Everything goes through this cycle over and over again. And that's how mathematics comes into the world. I call that the mathematics cycle. But it's, I might have given it the name. I actually may have been the first person that wrote it down this way, but this has been part of mathematics for thousands of years. The reason I expressed it this way was it's actually important today to think of it this way, because this is the only way you can make sense of how we do mathematics and how we need to prepare people to do mathematics. This part, by the way, is what we usually call a mathematical model. Once you've got it in the form of mathematics, which could be a system of equations, it could be some whatever it is, that's your mathematical model, and that's where you do mathematics. And the first 15 years of my career as a pure mathematician, I worked inside that box. I didn't care where the problems came from. I didn't care what happened to results after them. I was living in there and I loved it. It was great fun. And I did lots of calculations because I enjoy that kind of thing. But I was living in that box. I eventually started working outside the box, but there were still many people who prefer to work in that box, and we need people to work inside the box. Sometimes models become so useful that we forget they're models and we think of them as branches of mathematics. There's one of the first models, the first mathematical models that was ever developed. It was developed to draw the land barriers in the Nile Delta. Every few years the Nile Delta would flood, and when it flooded they had to redraw all the barriers between the land that were washed away. So they developed a system to represent the Earth's surface, a part of the Earth's surface, and the model they used became known by the name of geometry, from the Greek word geometros, which means earth measurement. So the process they had of planning out how to redraw the boundaries was done by creating a model. And you can see it's a model. There are rectangles there, there are some lines. This is just an abstract depiction of that with various numbers and angles put in. And we now think of this as a separate branch of mathematics, but it began as a model. A model that was so useful, you can apply it in many, many other instances, which is why it is thought of as a separate discipline. But it's just a model of representing things in the world. Okay, so how does that cash out in terms of daily work? What does it really look like? I mean, that's the sort of, the landscape view is what you can see at 30,000 feet. What happens when you're down there on the ground doing mathematics? What does it look like to do it? Well, here's how you do it. And this is true either of creating a new branch of mathematics, which is relatively rare, or working on a new problem in mathematics. When I worked with the NSA, and then these are all problems about dealing with data intelligently to form intelligence conclusions. You look for some sort of repeating pattern in the world, or some recognizable pattern. You study it. You study that abstract. The idea is to look at it in an abstract fashion, general fashion. You develop some kind of notation to describe that pattern, the notations of geometry. The language of algebra was introduced in 9th century Baghdad, essentially, to be able to scale up financial transactions. Instead of repeating the same financial transaction with slightly different numbers every time, they sort of developed a method of writing down formulas that you could just plug in the numbers, so you didn't have to go through the mathematics. You could literally just plug in numbers. And one of the techniques they developed to do that was a technique known by the Arabic term algebra, and algebra became algebra. And so out of 9th century Baghdad, a technique that was used to make trading more efficient became what we now call a branch of mathematics called algebra. But in a sense, algebra is just a model. It was a model of trading goods in Baghdad. Okay, you develop a notation, and it was very notational. You develop a notation to describe it. Using that notation, you further the study. Then, as the subject develops, you formulate basic assumptions that capture the fundamental properties. You sort of look at it in a detailed sense. Then you study those abstracted patterns. And then you start proving things to establish truth so that you know everything is rock solid logically. And then you develop procedures. And it is not necessarily as linear as this, but this is the general trend of things. You develop procedures that you and others can use to apply the results to the world. So you write down, here are the rules of algebra, here are the rules of differentiation, etc. So other people, without going through all of your thought processes, can simply apply those techniques. And then you apply the results to the world. So now you've gone from the world, you've gone round the cycle in a sense, and you're applying results to the world. Okay. This bit here, axioms, proofs, and procedures, that's mainstream mathematics. That's the stuff I did for 15 years. Because I didn't care about the stuff at the top and the stuff at the bottom. I just loved being in there. And it's a great subject. I occasionally go around to pure math conferences. As an onlooker, I can appreciate why everyone loves it, but it doesn't turn me on the way it used to. So that's the nature of mainstream mathematics. That is what school education focuses on. Because it has to, because you have to start somewhere, and you start with the procedures. University mathematics focuses on those. But as far as universities are concerned, and schools, that's mathematics. If you call it mathematics, it's the stuff in the box. But that's not what's going on today, because most of that stuff in the box is now, the mechanics has been automated. Using that method is what we do today. The technology has changed the way we work, which means we now actually think of mathematics as the whole picture, not just a bit in the box. First of all, most of the problems today require big picture solutions. They're just too big and complicated. Cloud resources, for the most part, and if not cloud resources, then specialized resources, can do all of the stuff that's formalized. So I and various other people that were present when this revolution took place started using this phrase mathematical thinking to talk about the whole picture. Start to finish, world to world, all of the steps. That's part of the procedure. And the reason we had to do that by zooming out and taking a bigger picture approach is the fact that most of that stuff that was in that box has been automated. We do sometimes do a bit of that, even working on practical problems. When I was working for the National Security Agency, I actually did a Euclid's Elements. I sat down and I wrote a set of axioms for context-based reasoning. Turned out to be valuable in some surprising ways. So I did a bit of that, but not in order to prove theorems, to do it in order to understand how context could play a role in making decisions. So that's kind of faded away. We just don't do that very more, and if we do it, it's for a different purpose. We rarely prove theorems. I didn't prove any theorems about, actually, that's not quite true. There is one theorem about proving, I didn't prove it, but a colleague of mine did. There is one theorem about context, which is the solution of the liar paradox. If you know about the liar paradox from ancient Greece, that can be solved in the logic of context logic. It's a very nice little proof. But that was just an interesting aside. And when we need to do the calculations, the procedures, those are all outsourced. So that stuff can be faded out as well. So all of that, the stuff that was in the box, and that's the box of mathematics, mainstream mathematics, as was known, has all faded away. That's now what we use this kind of tool for, Wolfram Alpha, and other tools. So that's in there, but that's a plugin. That's just an oracle that does stuff for us. The rest is what people are doing. And that's what people are good at doing. People are good at starting in the world and thinking about it, because that's how civilization developed, that's how Homo sapiens developed, and we're good about applying our thinking to the world. We've been doing that for hundreds of thousands of years. We've only been doing this symbolic math stuff for 300 or 400 years. So we've actually now gone back to the native state of people thinking about things, because we've got the tools that finally we now have to do the procedures. Okay, so how, in practical terms, does a mathematician think about a problem? When a mathematician comes in, what am I doing if I'm not solving equations and things? What am I actually doing? I'm applying this. It's the professional's toolbox. I've developed ways of thinking. Heuristics is an interesting word. Everybody knows what it means, but no one can really write down a good definition. So I went to Wikipedia and said, what does the society as a whole think the definition is? And here's the part that jumped out to me: a practical method not guaranteed to be optimal or perfect, but sufficient for the immediate goals. That's the tools that the professionals used all the time. They think in a way that gets them somewhere. When the time comes to be precise and get accurate answers, let the machine take over and give you the precise answers. But this is the thinking about it that solves the problem. You have to think intelligently about the problem without thinking about the way the solution is going to be gotten by the technology. And to show you this, I'm going to give you a puzzle. Every math talk should have at least one puzzle, and this is no exception, but this is a different sort of puzzle. I don't care if you get this one right. In fact, you don't have to tell anybody the answer, because I'm not interested in whether you can get it right. At a university like Huddersfield that's about engineering and technology, everybody in the room, every student at Huddersfield will be able to get this one right if I give them more than a few seconds. But that's not the point. What I'm going to use this puzzle for is find out what your human brain does if you take off all of the controls and let it solve the problem in its own way. You've all spent many years learning mathematics and problem solving. So the idea of this puzzle is I'm going to give it to you. It's just a simple, cute little puzzle about how much does something cost. The kind of puzzle you see on the backs of sort of cereal boxes and puzzle magazines and puzzle websites. Just a simple little puzzle. Some of you have probably seen it before. These are usually presented just to sort of challenge people, but I'm presenting it for a different purpose. I don't want to know, can you get it right? Because for sure you can. I want to know is, what does your brain think the answer is before you take charge of your brain? Because after schooling and living in the world, your brain will answer this question. So what I want you to do when I give you the question is just to yourself, think what the answer is. Don't try to solve it in the sense of just say, oh, the answer must be. That's what I want. What does the brain do? Because what I want to do is end up with an understanding of the things that the human brain does really fast and effectively, instinctively almost, learned instincts, and how that can be teamed up with computers that can get things right. Because that's the powerful combination we're talking about conducting the orchestra. So what can your brain do at the level of human creativity that a computer couldn't do? Okay, so the puzzle's coming up. One sentence. I'm going to actually read it out when it comes up. By the time I've finished reading it, you should have an answer. And don't sweat it, because you don't have to tell anybody the answer. I will tell you now, more than half of you will get it wrong. Because your brain will do something really smart, but the question is actually of a kind where the smartness of the brain can be fooled. So those of you who get the answer wrong can console yourself that your brain was really smart. It did something that was super, super smart. And you learned, certainly at school, if not anywhere, maybe somewhere else, you learned to think this way, and 95% of the time, it gets you the right answer. Okay? Single sentence, what's the answer you get immediately? A bat and a ball cost £1.10. The bat costs £1 more than the ball. How much does the ball cost on its own? No special pricing, time's up. So you should have now an answer to this question. You're probably already correcting your answer because some of you have thought, whoops, but your brain did something interesting. This is by far the most common answer. More than 50% of people, unless they're all very experienced mathematicians, and then they'll do something different. But here's the most common solution, and it's a smart solution. This is being a human being and being smart. You say, you look at the question, as you go through, that phrase costs more jumps out. Costs more, that means it's a subtraction problem. Your brain recognized a linguistic pattern, it recognized some words, and almost certainly, without, in fact, you may be, if you were in my generation, you were coached to look at exam questions this way. Look for key words, look for what you want to do. Costs more, it's a subtraction problem. There's only two numbers involved, £1.10, £1. You're going to subtract one from the other. The answer is going to be positive because you're a person, you know that nothing's for free in this world, so you subtract the smaller one from the bigger one. So you say, that's my data, subtract the smaller one for the bigger one because the answer's got to be positive, and the most common answer, more than 50% of the people say it's 10 pence. So that's the answer that people get. It's actually wrong. It's a heuristic. It comes from recognizing word patterns. Well, problems come to us through words. We deal with words. Very smart. Why waste time thinking about the details if you can just recognize the words? It's fast, and it usually works. You would pass, using this technique, you would pass an exam, because most of the questions, they would give you the right answer. But for this one, not quite. Here's another solution. This is the one we do, that we're taught to do in mathematics classes. And at least in my generation, I spent weeks in the, I guess when I was about 11 or 12, something around that time, the 11 plus that we had then, I was taught what they call basic algebra. Right? Let x be the cost of a bat, y be the cost of a ball. You know that x plus y is 1.10, 1.0, 1.1, £1.10. X is 1 more than y, so it's a pound more, so x is y plus 1. So you eliminate the x, and you get that equation, then you bring the y's over to one side, you've got 10 pence is 2y, so y is 5 pence. Okay, that's a procedure. It's slow. I mean, this is a simple one, so it's not that slow. But it always works. So if you wanted to write a computer program to solve this kind of problem, do it that way. Always works. Computer doesn't matter. But worry about it, and for a computer it will be very fast once it's got the data in. So that's another solution. Procedure, slow, always works. And for anything slightly more complicated, humans would start making mistakes. Probably not for this one. Here's the third solution, and this is the one that professional mathematicians almost all give. In fact, I think I'd seen this problem before, but I was actually given this as one of several problems. I was a guinea pig in a study by a cognitive psychologist who wanted to compare how Google engineers solve problems from the way professional mathematicians solve problems. So I went around mathematicians at Stanford and probably Berkeley, and mathematicians and engineers at Google, and engineers actually gave different answers, which was interesting. So this is actually turns out to be the answer that mathematicians give. And first of all, when he said, because he asked me the question, and I said, oh, 5 pence, well, actually I said 5 cents. It was in terms of dollars and cents. But so I said 5 pence, 5 cents. And he said, how did you get there? I said, I don't know, I just saw the answer was 5 pence. He said, oh, try. And we just had dinner. It was in a restaurant. That was his research technique. You know, his lab expenses was basically taking people out to fancy restaurants in Palo Alto, which is kind of nice for both of us. But then he got me to draw it on the back of a napkin. He says, well, just draw the best you can. So I ended up drawing something like this. I said, here's what happened when I read the sentence. Because he said, what did you do when you read the sentence? I said, I had an idea that it was a cost. So in my mind, there was an idea of size. It wasn't a rectangle, it was just some amorphous size, but he said, draw it. So I drew it as a rectangle. And I said, okay, it was some general abstract idea of a rectangle, but it had size. It was a quantity, some kind of a quantity. And I had the idea of the cost of the bat, which I knew consisted of the ball plus the bat. It was $1 more. So I knew that the bat was like the cost of the ball increased by $1. So I had these two quantities that came related. The moment those were formed, they were related. One was one thing and one was the other. But they came from the sentence. I just parsed the sentence, not in terms of keywords for procedures, but in terms of keywords for sizes. So it was very much like that, except I was using different heuristics to come at a different structure. It wasn't linguistic structure, it was quantitative structure, because I recognized that this was a quantitative problem. Okay, and there's nothing special about me, it's just what happens when you do mathematics for many years. You develop these abilities. And I knew that the sum of those things was $1.10, so I haven't done any arithmetic. All I do then is read off. So when I said I just saw that the answer was 5, I said, well, I've got these 3 blobs, and altogether they're 1/10, so each one of those must be half of the 10, because that's all that there is. So it was no deeper than the one on the left, but it was just a different heuristic. I just went into the numeric, to the quantitative thing. This was Numbersense. It's a numerical problem. So the answer was that the ball is 5 pence. Same answer as the procedure, but this was fast. I didn't even know I'd done it. I mean, that was the best I could do. And the guy that was running this study, I said, that's pretty well what everybody else at Stanford has said. That's sort of what they end up with, something like that. Google engineers have different, they think procedurally. I think relations and quantities. Engineers, not surprisingly, computer engineers, think in terms of procedural things, algorithmic things. I don't remember what he said about this one. His name, by the way, is Gary Antonick. He's actually one of the few mathematicians I know. He's the only mathematician I know who's from the English Channel. He was a world-class swimmer. He was part of the same team as Phelps when Phelps was coming up to Michigan State or wherever he was from. So he wasn't as good as Michael Phelps in swimming, but he's an interesting mathematician type cognitive scientist. Okay, so we've got these 3 methods. These have names. That's known as rigorous thinking. That's pre-rigorous thinking. And that's post-rigorous thinking. And this is where we need to be to conduct the orchestra. This is the more deeper sense of Numbersense. Okay? So how do we develop it? And this is the finale. We almost certainly have to go through rigorous thinking. There's a lot of stuff in cognitive science that sort of shows what's involved in doing this kind of thing. There's a lot been learned in the last 40 or 50 years. Almost certainly we need to go through rigorous thinking. We need to go through that tedious stuff with the equations, but we don't have to do 50 worked examples so we can get very fast at doing them and getting them right. 3 or 4 to the point where we think, okay, I get it. So you have to go through it to the point where you get it, and maybe it's more than 3 or 4. Maybe you have to do 10 examples, however many it takes, but it doesn't matter about getting it right because you're never going to do that to get it right. You have to use the machines that will get it right. So there's certainly lots of practice, but the jury is out as to how much. And for sure, those standard procedures over generations, they were optimized for people to be able to get the answer as fast as possible, as accurately as possible. You know, one of the reasons Hindu-Arabic arithmetic took off was it leaves an auditable trail. When you do Hindu-Arabic calculation in the standard layout, it generates its own audit trail. So you immediately produce a certificate of the answer. Very important if you want to do international trading, that you don't have to have a separate certificate of authenticity from the actual calculation. That was one of several reasons why Hindu-Arabic arithmetic took off in the 13th century. Automatic audit trail. But everything's changed now, so we need to automate, we need to optimize. And Hindu-Arabic arithmetic, the algorithms are optimized for procedures, procedural execution. They're not optimized for understanding. So we need to use algorithms that bring out the understanding. Interestingly enough, versions of the long division algorithm, if you do the version correctly, it really brings out the understanding of place value arithmetic. So some of the old stuff is still useful. You just have to repackage it and reuse it in a more sensible way. So that's the goal. And you almost certainly do need to go through quite a lot of that. But you don't need to do it with artificial examples. You can do it with real examples. You can give groups of students, and I've done this with high school students, university students, non-science students at universities, non-engineering students, and they can work on real problems, significant problems, problems out there in the world. You know, how does United Airlines or British Airways price the ticket you buy? That is within the scope of any high school student. You can reverse engineer the algorithm that an airline uses to price tickets. You go on the web and you pretend you're ordering tickets, and you order a bunch of tickets to different places, or you order different types of tickets. You look at the prices, you look at the data, and you start to analyze the data, and within however long it would take you, it could take you a few weeks, it could take you 1 week, you can come up with a pretty good insight in the costing structure of British Airways as a high school student. Just collect the data and analyze it. I'm actually doing that for package shipments around the world with a class here at Huddersfield. We finish it tomorrow. We've been looking at how do you reverse engineer the way packages are routed from place to place when you order something from Amazon or from Apple or whatever, and it gets shipped around the world. And again, you can order things, you can track the packaging, and you can reverse engineer the algorithm. Real problems, interesting problems, collect your own data, do their own thing. It's interesting, it's fun, and it's valuable because it takes you through this process of developing good heuristics. So content matters, but not that much. It might as well be relevant content, because why not? But ultimately, it doesn't really matter because it's about the way of thinking. It can be absolutely anything, whatever. When I was working for the NSA, they didn't let me anywhere close to real intelligence data. I had what they said was fake data that they used for training new analysts. But I could have done the same research for Sainsbury's, with Sainsbury's sales data. It didn't matter. It was just a data set. Okay, that's what I want to leave you with. That's what being a mathematician is now. Of course, it's easy to stand there and pretend you're a conductor, but musicians will know that you're not unless you really know what you're doing. So you cannot fake being a mathematician. Actually, if you do fake it well, you can earn a fortune as a consultant, and any company that hires you deserves to have been fooled by that. But it's not easy to do, but it is what we do. That's what mathematics is now. It's conducting an orchestra. A version of this talk appears among the videos on that website. This is my new centre at Stanford, and there's a version of this talk that you'll find there. That's the story for today. Thank you.